Bismillahirrahmanirrahim. Assalamu alaikum. So yesterday we left off at the first chapter of Clojure from the ground up, that is the welcome chapter, and basically we set up our environment, mostly Windows PC environment for Clojure programming, and we tried to run some code in REPL and learn about the basics of symbols and how Clojure uses its prefix notation for programming and tree-like structure to create programs. Today we'll probably finish the second chapter or the first chapter, the basic types, and hopefully we'll get over it rather quickly. But before doing this, I was thinking about doing this Clojure workshop tutorial, or workshop. It's kind of like a so my teammate Thiago, who's also a member in the team Prometheus, he referred to me this course that's currently free, and I'm thinking about doing this because there's also detailed instruction on how to set up your environment, for example, for REPL, etc. To me, this looks the Clojure from the ground up looks a little outdated. Yeah, it was written in 2013, so I guess here we'll have detailed instructions and more up-to-date instructions on how to set up an environment better, and they also have video instructions as well. So first let's try to do a couple of exercises here, go over some of these topics, and then we'll also try to go quickly over this chapter as well, inshallah. So let's start from here. So basically, thank you for purchasing. Okay, there are hands-on elements in course which are exercises. They have a step-by-step reference implementation followed by a screencast. So the recommended way is to first follow the step-by-step instructions and then watch the screencast, so as to get a better idea of how to do something. Taking this approach lets you hack. Okay, yeah, basic introduction and how to move about. Yesterday we set up Java on our environment using scope, yeah, we also installed Clojure. We installed this line.bat as well. We added it to our environment path, so nothing much to do. Yeah, we have to clone this repo as well to follow along. So let's quickly clone that and let's continue. Clojure workshop, authors, technical reviewers, got it. So yeah, it seems pretty detailed and well thought out and relatively new, like 7 or 8 months ago. So let's see how it goes or how much better it is than the other one, if any. So first let me change into my workspace directory, and then we'll git clone the Clojure workshop. While it is being done, you completed workshop onboarding, continue. So overview. By the end of this lesson, you will be able to use the REPL and work with functions in Clojure. We kind of already do that. Okay, explain the basics of creating Clojure program. Let's see how it goes. We start by getting REPL. Also allows you to explore code and documentation by yourself, so it is an excellent place to start. After the quick dive in the REPL, we describe in more detail how to read and understand simple Lisp and Clojure syntax. With syntax can sometimes appear unsettling. We then explore fundamental operators and functions in Clojure. Have you ever ended up entangled in the spaghetti code of an object-oriented application? Yes, I have. Many experienced programmers would, yes. And at some point in their journey or career would reconsider the foundation of their programs. They might look for a simpler, better alternative to object-oriented programming, and Clojure is an appealing choice. It is a functional, concise, and elegant language of the Lisp family. Its core is small and its syntax minimal. It shines beauty of its simplicity, which takes a trained eye to notice and ultimately understand. Employing Clojure's more sophisticated building blocks will allow you to design and build sturdier applications. Whether you are a seasoned programmer or a novice, hobbyist or a professional, C# wizard or Haskell ninja, Haskell, I guess. Haskell most probably. Learning a new programming language is challenging. It definitely is. It is, however, a highly rewarding experience that will make you an overall better programmer. In this book, you will learn by doing and will ramp up your skills quickly. Clojure is an excellent choice of programming language to learn today. It will allow you to work efficiently using technology built to last. Clojure can be used to program pretty much anything from full-blown client-server applications to simple scripts or big data processing jobs. Okay. Personally, I prefer something that is not JVM based, because for me JVM feels a little slowish as compared to other compiled languages like C++ or Rust, etc. There's a dependency, like, because of the JVM environment and the whole garbage collection thing. But let's see how well Clojure is. REPL basics. Welcome to Clojure. Read REPL, a command line interface that we can use to interact with a running Clojure program, in the sense that reads the user's input where the user is. You evaluates the input by instantly compiling and executing the code and prints results. The read, eval, print three-step process repeats over and over again until you exit the program. The dynamism provided by the REPL allows you to discover and experiment with a tight feedback loop. Your code is evaluated instantly and you can adjust it until you get it right. Yeah, that's one thing I really love about REPL, that you can really quickly experiment with different ideas and see what works and what doesn't and how it behaves. The dynamism provided, yeah, many of them, notably others such as Ruby or Python. Yeah, I have a lot of experience in Python as well as Julia, and they both provide a very spectacular REPL support. But in Clojure, the REPL plays an exceptional and essential role in the life of the developer. It is often integrated with the code editor, and the line between editing, browsing, and executing code blurs towards a malleable development environment similar to Smalltalk. I haven't worked in Smalltalk before, but let's start with the basics. Throughout these exercises, you may notice some mentions of Java. This is because Clojure is implemented in Java and runs in the JVM. Clojure can therefore benefit from a mature ecosystem while still being a cutting-edge technology. Clojure is designed to be a hosted language, and another implementation called ClojureScript allows you to execute Clojure code on any JavaScript runtime. This hosted language implementation choice allows for a smaller community of functional programmers to strive in an industry dominated by Java, .NET Core, and JavaScript technologies. Okay. In this exercise, we will perform some basic operations in the REPL. Let's go started. Open terminal and type CLJ. This will start a Clojure REPL. I wonder if this will work for us as well. Yeah. But before, I guess they missed something, because it didn't say anything about setting up CLJ anywhere here. Yeah, they said about using lane and lane REPL, but nothing about CLJ or how to set it up. Maybe they Getting around in the REPL. Nope, doesn't seem like. Yeah, that's weird. I was thinking that this will be more detailed and step-by-step installation instructions with consistent program usage, but here I think it should be lane REPL or CLJ. Open a terminal and type CLJ. Probably for Windows it's different, and for Mac or Linux this will be available. I don't know. Okay, the first line, which in don't worry if your version this and they go through together, would be compatible with any version of Clojure. The second line displays the namespace we are currently in user and prompts for input. A namespace is a group of things such as functions that belong together. Yeah, I have a little bit of understanding or idea of what namespaces are because of C++. A namespace is a group of things such as functions that belong together. Everything you create here will be in the user namespace. By default, the user namespace can be considered your playground. The REPL is ready to read. So here we are in the scratch.core namespace. I guess this is the namespace. Let me quickly verify it. ls cd scratch ls. Is there a folder named store? Dogs, resources, source, test. Okay. User. I wonder how to start this. Hello, Apple. Wait a minute. CLJ Apple Windows. That's taking a while. Maybe there are some setup instructions here. Nope. REPL Lenin. Maybe we need to install Clojure through scoop. Let's try that. Scoop search Clojure. Yeah, probably we'll have to install to Clojure, and main REPL didn't set it up for us automatically. On Windows, so it's an early release version. Windows isn't really supported or is first class citizen here, and yeah, that's shame. Scoop Clojure. It was updated 5 days ago. In order we have to install scoop first. Okay, scoop install scoop bucket add, and we have to add in the bucket. Install Java runtime and compiler. Adopt OpenJDK LTS hotspot. Official Clojure tool. Well, let's try to add this bucket. Paste it, and then let's try to install the Clojure using Scoop. I like Scoop more because you can easily update all the softwares or a single software using a single command line, so it's better that way according to me. And then we can install Scoop Clojure and update it if necessary, but I don't think this would be required because probably this will install the latest one. Yeah, most probably this will install the latest version, but still we'll run this as well. Okay, CLI dot installing Clojure, how much space? 16 MB. Clojure tools, and then hopefully CLJ will run and it will give us basic user REPL, user namespace REPL. So let's try to evaluate an expression. The output is hello world as expected, or hello REPL. In Clojure, literal strings are created with double quotes. Literal is a notation for representing a fixed value in source code. Let's see what happens if we type in multiple strings hello again. Okay, two separate lines. No. So if we type hello, two. Okay, this printed on a separate line. You have just valid two expressions. So expressions can be written on the same line. Yeah, that's nice. First it evaluated this expression and print the result out, and then it evaluated this expression and print the result out. Each result is printed onto separate lines. Now let's try a bit of arithmetic. For example, 1 plus 2. The output is as follows. Now this is 1, plus is a symbol, and this is the value of the plus as we've seen yesterday, and 1 plus 2, it won't evaluate it. The output of Clojure evaluated 3 components, that is 1, plus and 2 separately. Okay, now I see, now understand really. So this is one expression, this is second expression, and this is third expression, and it evaluated each and every one of them. What if we say this is a single expression? Yeah, so it's trying to cast long one. It's thinking that this is a verb or action, and it's trying to cast it to plus, I guess. Yeah. Separately when extended, because this plus symbol is bound to a function. A plus symbol is bound to a value, and the value of a function. A function is a unit of code that performs a specific task. We don't need to know more for now, except that the functions can be called or invoked and can take some parameter. The function's argument is a term that's used to design the value of a parameter, but those terms are often used interchangeably. To add those numbers, we need to call the plus function with the arguments 1 and 2. Okay, we need to call the plus function with the arguments 1 and 2, which are, yeah, we've seen that yesterday. You will soon discover that many basic operations are a real part of programs, and so are just simple functions in Clojure. Okay, so in C++, this is part of the language syntax. Plus is a symbol that's defined in the C++ specification, but in Clojure, most of these will be simple functions. Okay, let's try a few more examples of basic arithmetics. More than 2 formulas, so adding 1 plus 2 would together look like. So this will apply this function on each and every one of these. 1 plus 2 plus 3. The other basic number used in try and type the following expression: -3 2. This will evaluate to 3 minus 2 3 times 4 times 1. So 3 times 4 would result in 4 3s are 12. Here it will be 12. Then it will apply again on the two arguments, that is 12 and 1. Okay. After typing in the room, you should try a few more examples here to be experimented with. Let's see if it works now. Clojure. I guess we'll have to restart our no value name module found. That's strange. CD workspace. Clojure. Yes, something is happening. Yeah, it's working now. Clojure, and we can type things here. That looks good. You should now to ask the following link. Would you like to down? Okay, so there's print line function as well. Print line column and nil. Why nil? Printing a nil, so that was returned. Okay, this will print first. It will print this and then it will return something, and that is nil. But why does it need to return something? Print line. The text that was merely a side effect of this function will leave the Clojure equivalent null or nothing, that is the absence of meaningful value. Print without a new line and print line are used to print objects to the standard output, and they return nil once they are done. Okay, now we can combine those operations and print the result of a simple addition. 1 plus 2, and then we print it and it returns nil. The value of 3 is printed, and the value of nil was returned by this expression. Notice how we have nested those forms or expressions. This is how we change functions in Clojure. You can exit by pressing Ctrl D, or you can type exit 0. Exit 0, or do I have to type system/exit 0? Yeah, system exit. Got it. REPL, complete and continue. Let's quickly see the quality or how they name these concepts. Quality.
In this exercise, we'll perform some basic operations in the
I
Clojure
usually
REPL.
listen at
To start, open a terminal
2x or
and
3x
type
if possible.
CLJ. That will start the Clojure REPL. The first line of your output is the version of Clojure. In this case, it's 1.10.1, but don't worry if your version is different. Our exercises will be compatible with any version of Clojure. The second line displays the namespace and a prompt for your input. A namespace is a grouping for things like functions that belong together, and everything you create here in the user namespace by default. The user namespace can be considered as a playground. Your REPL is now ready to read, so let's try and evaluate some basic expressions. In Clojure, a literal string is created with double quotes, and the literal is just a notation for representing a fixed value in source code. In this case, we have a literal for hello REPL, and when we put this expression into
I think
Clojure
they
REPL,
don't
Clojure
need
REPL
to
returns
listen
to us
to
the
this
result of
for now because
evaluating
everything
it,
is
which is
clear
exactly the same literal. Now, let's see what
till this point. Let's move on to the second exercise. Getting around in the REPL and the introduce to navigational key bindings and commands to help you survive. Start by opening the REPL again. Yeah, we've opened it. You notice how you can navigate the history of what was typed earlier in the preview by Control P or Control N, or the down upper or downer. I'm using upper or downer. The Control P is for previous, and Control P isn't working for me, neither is Control N. So it's going to be up arrow or down arrow, and we can go back quite a bit. Okay, you can also search case sensitive through the history of the command you have entered. plus Control R and then hello. Control R and then hello. Control R doesn't work for me either. How about Alt R? No. Shift R would just enter R but capitalized. So I don't know why these shortcuts aren't working for me. Let's try command line, that is cmd.exe instead of PowerShell, and maybe the shortcuts will work there. And command line doesn't recognize CLJ. Perfect. Okay, so this doesn't work. No value which increments to 1, the return value which is indeed 10 plus 1. That is bound to the result of the last expression. Okay, so if we might add 2 plus 8, and if we do *1, then it will give us the last evaluated result. But what if we do 8? So *1 will give us -6. How about *2? It also gives us -6. *3. So we will bound to the second and third most recent values of that tuple respectively. The *2 is so *1 gave us 10, but when evaluated this -6, *1 gave us -6, but *2 now refers to this -6, so it's giving us -6, and *3 refers to this -6 and giving us -6. So if we do this and then if we do *2, it will give us this value, but if we do 3, then it will give us 10. Yeah, that makes sense. You can also reuse those special variable values within other expressions. See if you can follow the entire this sequence of commands. Oh, that's nice. So we can evaluate what the last expression calculated. That is good. To clear screen, Control L, and I doubt this will do anything. Control Shift L, Control Alt L, Alt L. Never mind. Okay. Why are these not working for me? Tuple is story which contains the result of the last exception. At the moment it should be nil because no exception has occurred yet. But let's and *E would give us the result of the last exception, which doesn't look good at all. Another use of variable that is available contain details about the expression unmatched delimiter. It shouldn't. Yeah, where it should have given the arithmetic exception, but instead I mistakenly typed as /1 instead of /1. So may have slightly error. For example, if you try to divide by 0 in Clojure script, it will not throw an exception, instead return the infinity value. Okay. The doc, find doc, and apropos functions property, or what's it in the short form of functions, are essential REPL tools for browsing through documentation. Given that you know the name of the function you want to use, you can read its documentation with doc. Let's see how it works in practice. Start by typing doc inc. Returns a number 1 greater than num, does not auto promote longs, will throw an overflow. Okay. As a document we can pass Let's try doc. So we can either pass something or we can pass no arguments returns the empty string, with one argument returns x.toString, and string nil returns the empty string, with more than one argument returns the concatenation of the string length. Okay, if we pass more than one string, then it will concatenate those, and if we don't pass anything, it will return an empty string. We can pass multiple argument string I, it will concatenate those without putting any spaces. And yeah, there are little spaces here, so it will format it correctly. But why do this? Okay, prints the fully qualified name of the function including the namespace. Clojure is the namespace here, or core is the namespace. On the next line, the possible sets of parameters, and then finally in this function's fully qualified name is clojure.core/string, which means that it is in the clojure.core namespace. So this is the whole namespace name. Things defined in clojure.core are available to your current namespace by default without you explicitly having to require them. This is because they're fundamental components for building your program, and it will be tedious to have to use their full name every time. Okay, documentation of the doc function clojure.repl. It's defined in clojure.repl. So most probably we won't be able to use it in a editor, I guess. Clojure.repl/doc. Name macro prints documentation for var on special form given its name, or for a spec if given a keyword. This function is in the clojure.repl namespace, which is also available by default in your REPL environment. You can also look at the documentation of namespace as its documentation suggests. Your final program would typically not use the helpers in the clojure.repl namespace, for instance doc, find doc, and apropos doc clojure.repl. Let's try that. Doc clojure.repl. Clojure utility is meant to be used interactively as the REPL. What is apropos doc? Syntax error. Given a regular expression or stringable thing, return a sequence of all public definitions and all currently loaded namespace that match the string or pattern. Purpose. When you don't know the name, but you have an idea of what the description or name may contain, you can search for it with the find doc helper. Let's try and search for the modulus operator. No luck, but there's a catch. Find doc is case sensitive, but the good news is that we can use a regular expression with I modifier to ignore the case. So regular expression, you don't need to know more about regular expressions for now. You don't even have to use them, but it can be useful to ignore the case when searching for a function you can write them with. So we have to add the pound symbol or hash symbol before the string, and then we can write our regular expression in parentheses. Clojure.mod. Let's try that. Find doc, and then we specify that there will be a regular expression in there, and then we say that don't worry about the case sensitivity. Find doc modulus. It's taking quite a while. Oh, my bad, I had to close the modulus of num and div truncates toward negative infinity. 7/3, its modulus is mod 2/8, probably. My bad. Mod 2 and 8. 2. And mod 8 and 2. 0. Yep, works fine. To search for functions by name, thereby yielding a more succinct output. Say we were looking for that performs the case of a given string of characters. So corpus case, there's lowercase user Clojure.string / uppercase. Why does he specify the whole namespace here? Won't it work the other way? Please note that this function is in the Clojure.string namespace, which is not referred to by default. You will need to use its full name. Okay. Until we learn how to import and refer symbols from other namespaces. The approximation kind of thing. Function to search for functions by name. Okay, this is search for functions by name, and this is find doc, search for documentation. Let's move on. I was hoping that they would give a detailed instructions or a guide on how to set up your coding environment. For example, here I have Visual Studio Code.
We will introduce a few navigational keybindings and some documentation commands to help you work with the Clojure.
Yep. Like how to set it up for Java, which is the REPL or environment for programming Clojure in Visual Studio Code. But anyways, performing basic operations. In this activity, we will print messages and perform some basic arithmetic operations in the Clojure REPL. These steps will help you complete this. Open the REPL, print the message. I'm not afraid of parentheses. Yep. And for printing, we don't have to, use print etc. Just this would work fine. We can use something like yep. Okay, add 1, 2 and 3 and multiply the result by 10. So first at the end we have to multiply by 10, so 10, and then we can first it would evaluate the inner loops, so add 1, 2 and 3 and what the result is, then multiplied by 10, so it should be 60. Yeah. Following in fixed notation, you should obtain the following result: 42. As it now, or it's 10 minus 3. Result by 10 minus 3 multiplied by 10 minus 3. My bad. I guess this will take some time to get used to this infix notation. Prefix notation. This is the infix notation, and after several years of programming in C++ and Python etc., you get really used to it and just start typing this without thinking much. Print the message. Well done. Well done. Yay, I'm so motivated. Next, and I wonder why it's so slow. Evaluation of Clojure code. Okay, this was the activity, these are exercises, then there will be activity. Clojure is a dialect of Lisp, a high-level programming language that was designed by John McCarthy and first appeared in 1958. One of the most distinctive features of Lisp and its derivatives or dialects is the use of data structures to write the source code of programs. The unusual number of parentheses in Clojure programs is a manifestation of this, as parentheses are used to create lists. Here we will focus on the building blocks of Clojure programs, that is, forms and expressions, and briefly look at how expressions are evaluated. The term expressions and forms are often used interchangeably. However, according to the Clojure documentation, an expression is a form type. Every form not handled specially by a special form or macro is considered by the compiler to be an expression, which is evaluated to yield a value. Every form not handled specially by a special form. I guess we'll learn more about this later on. We have seen how literals are valid syntax and evaluated themselves. For example, hello would evaluate to hello, and 1 to 3 would evaluate to 1, 2, and 3, all separate expressions. 3 different expressions. We have also learned how to invoke functions by using parentheses, plus 1, plus 2, plus 3. It is worth noting at this point that comments can be written with this at the beginning of line. Any line starting with this will not be evaluated. Okay. This is a unique place for a comment. Functions are invoked according to the following structure: comment, operator, operand 1, operand 2, operand 3. For example, this multiplied curve. Take note of the following from the preceding example. The list noted by opening and closing parentheses is evaluated to a function call or invocation. When evaluated, the symbol results to function that implements multiplication. 2, 3, and 4 are evaluated themselves and passed as arguments to the function. Consider the expression you wrote in activity 1 when performing basic operations. Yeah, it's kind of same. Can also help to visualize the expression as a tree. So there's first list, and then when we multiply two lists, that is the result of these two lists. So here these lists will evaluate to some expression or some value, and this list will evaluate to some value, and then we multiply those lists and it will evaluate to some value. Evaluating the expression consists of reducing the tree starting with the offshoots, the innermost list. So if we look at it like this, then the bottommost or the deepest node level, which becomes quoted in the term. S expression or symbolic expression is often used to designate those types of expressions. You may come across it again, so it is good to know that an S expression is a data notation for writing data structures in code with lists, as we demonstrated previously. So far, we have only used literal scalar types as operands to our operators, which hold one value such as numbers, strings, booleans, and so on. We've only used list to invoke functions and not to represent data. Let's try to create a list that represents data but not code. 1 to 3, and then we cast to Clojure. Okay, an exception was thrown because the first item of the list was not a function. There is a special syntax to prevent the list from being considered as the invocation of a function, the quote. Okay, the escape character that we learned about yesterday. Creating a literal list is done by adding a quotation in front of it, so let's try again. Here this would create a literal list instead of trying to evaluate it. Great, by preventing the evaluation of the form, we can now write a literal representation of lists. This concept will help us get ready for what we are going to cover next. It is, however, fascinating to notice at this point that Clojure code is made up of data structures, and our programs can generate those same data structures. Code is data is a famous thing in the Lisp world, and a powerful concept that allows your program to generate code, known as metaprogramming. If you're new to this concept, it is worth pausing for a minute to think and admire the sheer beauty of it. We will explain metaprogramming techniques. Yeah, so the idea is to generate code or write code that generates code. Write a program that writes other programs. Okay. You can continue. Let me cancel that part. Working with if, do, and when. So far, we've been writing code that compiles with the simpler tools of evaluating Clojure code, but there are some behaviors that cannot simply be encoded with normal functions. For example, arguments that have been passed to a function will always be resolved or evaluated. But what if we do not want to evaluate all the operands of an operator? That is when special forms come into play. They can have different valuation rules for functions when the source code is read by Clojure. For example, the special form if may not evaluate one of its arguments depending on the result of the first argument. Okay, there are a few other special forms that we'll go through in this section. When, which can be used when we are only interested in the case of a condition being truthy. The value is truthy when considered true in the context of a Boolean expression. Why not use just true here? Do, which can be used to execute a series of expressions and return the value of the last expression. Def and let, which are special forms that are used to create global and local bindings. Fn and defn, which are special forms that are used to create functions. Okay, basic special forms. These are forms. Working with if, do, and when. In this, we will evaluate expressions using the if, do, and when forms. Let's get started. If true, yes, no. Basic conditional statement. If something is true, print this, do this, else do that. If true, yes, no. If yeah. The special if form evaluates its first argument. If its value is truthful, it will evaluate argument 2, otherwise or else it will evaluate argument 3. It will never evaluate both arguments 2 and 3. We can nest expressions and start doing more interesting things. Okay, this rind. This will evaluate rand, where this will give a rand. Okay. In this case, the command will not be executed, only a random number between 0 and 1 will be returned by the rand function. But what if we wanted to do more than one thing in our branch of the condition? We could wrap our operation with do. So, more than one thing. Do expressions, special form evaluates the expression in order and returns the value of the last. If no expressions are supplied, returns nil. To use the special form do, type the following expression do. If this is true, then do that, and return the value of this. Okay, but can't we do if with multiple statements, or do we always have to have a single statement or expression in an if condition? All the expressions before there were evaluated, but only the value of the last one is returned. This does not look very useful with expressions that don't alter the state of the world, so it would typically be used for side effects such as logging or any other kind of IO. You don't have to take my word, so let's experiment the side effects of printing to the terminal. Okay, do print line proof. A proof was executed, then it returned no. And this too. Finally, we can combine the use of if and do to execute multiple operations in a conditional branch. Okay. So it was just simply to all these. Yeah. I wasn't looking closely at this. This isn't a conditional statement or conditional expression or condition. These are just all expressions, and we can combine these to run conditional statements with multiple expressions. Got it. If true, do print line, calculate a random number, and otherwise print 3. Okay, technically you could also omit the third argument, bring back the previous expression, and remove the last expression, that is +1 +2. Okay, so no nil condition or no else condition. Sorry, we have better construct variable the when operator. Instead of combining if and do when, you are only interested in doing work in one branch of the condition, is use when. Okay, when true, then print all these things. Got it. Hidden usage of special forms. These are called forms: if, do, when, etc. Well as conditional expressions. Got it. Let's skip the video. Using def and let. I guess this is moving relatively faster, quicker than the Clojure from the ground up. Let's see what we will learn next. Using def and then creating simple functions. We are learning to create functions as well, predicting the atmospheric carbon dioxide. That will probably use functions and if else. The truth is simple: comparing values, data types, and immutability. Here we're using maps, sets, vectors, which we learn in the Clojure from the ground up second chapter. And then functions and depth. So let's quickly finish this, and then we will move over to Clojure from the ground up. And later on, if we feel like it, we can complete this as well: data types and immutability. For binding, in Clojure we use the term bindings rather than the variables and assignments because we tend to bind a value to a symbol only once. Under the hood, Clojure creates variables, and so you may encounter this term, but it would be preferable if you don't think of them as classic variables or values that can change. We won't use the term variable anymore in this chapter as it can be confusing. You can use def to define global bindings and let for local bindings. So if you're coming from C++ or Python, etc., then you know what are local variables and global variables. So they use binding here to represent a variable because according to them the value that the variable or the symbol that gets bind to a value is only bind once. So while in C++ or Python values can change, the variables can change their value. Using def and let, we will demonstrate the usage of the def and let keywords, which are used to create bindings. The special form def allows you to bind a value to a symbol. In the REPL, type the following expression to bind the value 10 to the x symbol. So def x10. So it's in the user namespace and value is 10. If we write x, it would evaluate to 10. If we write this, then it will evaluate, it will simply print out its name and won't evaluate the result. So this is a reference to the var you have just created. The user part indicates the namespace where the var is defined. Got it. Technically you can change the binding, which is fine when experimenting in the REPL. Okay, technically you can change the binding, which is fine. It is not recommended in programs because it can make it hard to read and complicated. And if not, it would be better if you just consider such a binding as a constant. But what's stopping me from changing it along the way? Like in C++, for example, if variable is defined as const or constant, then I can't really change it. It would give me a syntax error, compile time error. But here I can change it, so it's not really a constant. I'm confused. Index. Wherever def is invoked, it will bind the value to the symbol in the current namespace. We could try to define a local binding in a do block and see what happens. So if you know about blocks, for example from C++ or scope, there's local scope and global scopes. I guess the idea of scoping is also present in this Lisp language. So if we bind def x42 here, and then print line x, it would print 42. But now if we print x, it would, okay, really I thought it would still be 20. Bindings that are created by def have an indefinite scope, dynamic scope, and can, okay, these are the global ones. Okay. So if we do def, instead of def, if we do let and change it to 4, okay, its syntax is different. I should read first, then try to tinker with the code. The bindings that are created by def have an indefinite scope or dynamic scope and can consider global. They are automatically namespaced, which is a useful trait to avoid clashing with existing names. If we want to have a binding available only to a local scope or lexical scope, we can use a symbol from let, type the following to create a lexical binding, the y symbol. Let y is 3, and line y, 10 times y. So let y equal to 3, and then line y, and then multiply y with 10, 3 and 30, and if we try y, there's no y present in this context. Let takes a vector as a parameter to create the local bindings and then a series of expressions that will be evaluated like they are in a do block. So let defines its scope as a vector is similar to a list in the sense that they both are a sequential collection of values. Their underlying data structure is different, and we will shed light on this in chapter 2, data types and immutability. For now, you just need to know that vectors can be created with square brackets. Evaluate the y symbol and there is thrown because we are now outside the let block. Type the following expression to create a lexical binding of x to the value of 3, and then see out effects the indefinite global binding of x that we created in step 4. Yeah, I can imagine what the result would be. So if we print the value of x inside the let block, it would be 3, but outside the let block, let's print line x, it would be original 42. Nil is returned by the print line function. You can create multiple local bindings at once with let passing an even number of items in the vector. Type the following expression to bind x to 10 and y to 20. X to 10, y to 20. String combines the strings, so we'll return a string. Combine the console and we'll write the following expression. Def message, let's add them all. User let, wow, let's try this. and let's add them all. So this would create a global variable or global binding called message, and then we will create a local binding where x is assigned to the result of 10 times 3 and y is assigned the value 20 and z is assigned the value 100, and then we will print the message which is in the global scope or namespace. What do this? Global binding, global scope, I guess. Scope seems like the right word. Oh, block, global block. It's important to learn the vocabulary of the language that you're learning. Syntax error. Macro expanding Clojure.core x 10 y20 z is equal to 10. When did I said, oh my god. Let x y z 100 z is 100 and front line message and plus x y z. Let's add them all 150. So that's how you write program in Clojure. I don't think I am liking this syntax very much till now, but for now I haven't seen the power of using this syntax really, and I haven't tinkered with or tried solving some problems with this, so most probably this will change this liking. Using def and let's skip the video. Creating simple functions with fun and defen. The special form that's used to define function is fn. Let's jump right into the creating a f function. Type the following expression in your f function. I guess these must be the arguments that it takes or the expressions that it performs. We have just created the simplest anonymous function which takes no parameters and does nothing, and we returned an object which is a function with no name. So this function has no name as well. So this is anonymous function. If you come from JavaScript, most probably you know about these, are using these for a while, or other programming languages like Dart or Python, etc. Create a function that takes a parameter named x. So this is the parameter and this is the expression, and return its square value multiplied by. So I guess to run multiple expressions we have to use the do block here, most probably. Let's try writing this function which takes a single parameter x and returns the square. And how so if you remember this, can we evaluate it using something like I want to use that function with the value 2. No, doesn't work like that. The first item will be invoked, so we can call our anonymous function with wrapping it by providing an argument as a second item of the expression. It's doing the same thing. So will it work? Probably this will work. Nope. Here's the function. We want it to evaluate this. I guess I should do 3. Can't we evaluate the function like that? One. So this is the function, and I want to evaluate it. About *1. About 2. Yeah, it's working now. We can use now it's not, because yeah, it's tricky because now when I where's the here when I *1 2 here, it's still referring to this, I guess. And now when I *1 4, now it's referring to this. So 4 and 4 doesn't really do anything, so I need to refer it to 3 steps above, to this function or this thing, and then it will evaluate to 6. First time will be invoked, so we can call on by wrapping it. Now this is but not value. If we want our function to be usable or testable, it would be better for it to have a name. We can create a symbol in the namespace and bind it to the function. Use def to bind the function returned by the special form fn to the square symbol. Form. I'll have to keep in mind these keywords: special form, and forms that we've learned till now are if, do, when, fn. What else? Def and let. Are these forms as well? Defined by the special form. Now def, this will bind square to this function, and then we can use square to calculate different. Square 2 would result in 4, and then we squared that, it would result in 16, and then we squared that, it would result in 256. Built-in macro is born out of necessity. Defen. Create the square function with defen instead of def and fun. So def square and then fn. Instead we just define our def n. This would bind square to this function expression where x is the number of inputs, or x is the arguments, and this is the expression evaluation. First, in a vector, we have already learned the vectors are collections, so you can add more than one symbol to the arguments. Vectors, the value that passed when calling a function, will be bound to the symbol provided in the vector during the function's definition. So let's try to create a function def n sum, and it should input, how do you say, a number of different arguments, like multiple, let's say x and y for now, and it should, I want to try the do function as well. Do expression So it should a plus xy and then print it as well. Print what? Let's see. Just print summed do indefinite. So if we try now sum 1 and 2, summed nil. Let's try to print this as well. Print line. So sum d summed. Got it. And can we pass multiple values to this as it is? Nope, we can't. So we'll have to chain it. 1, 2, 3. But shouldn't it print it multiple times? Like for example, first it was called for sum 2, 3. Okay, it returned nil, I guess. We didn't learn about returning something yet. You develop a function with the name meditate, which takes 2 arguments, a string s and a boolean com. You print an introduction message and return a transformation of s based on com. Define meditate as com. And okay, we didn't need to do the do thing. They all have implicit multiple block support. Print line Clojure meditate version 1 if com, then capitalize S, otherwise string uppercase S, and add a exclamation point. And the function body contains 2 main expressions, the first of which is a side effect with print line, and the second of which is the if block, which will determine the return value. If com is true, it will politely return the string capitalized with the first character converted into uppercase, otherwise it will shout and return the string with all its characters to uppercase, ending with an exclamation mark. Yep. Let's try and make sure that our function works as intended. Meditate in calmness lies true pleasure, and for the second parameter we return true, and otherwise we return false. If we call function with only first parameter, it will throw an exception. This is because the parameters that we have defined are required. One last thing, to enter initial tour of this function is the docstring parameter, which provided to define it will allow you to add a description of your function. Add documentation to your square function by adding a docstring just before the function arguments. Got it. That's how you add a docstring. Define function name or the value or the symbol the function should bind to, and then the docstring, documentation of the function, and then the input arguments, and then the thing that it needs to perform. I guess it's not never mind. Remember, the needs to come before the function argument. If it comes after, the string will be evaluated sequentially as part of the function body and won't throw an error. It has valid states, but it will not be available in the doc helper and other development tools. It is good practice to document the arguments with backticks like we did with X, so that development tools such as NRD can recognize them. We'll take deeper function. Let's skip the video. And yeah, let's try to do this activity. Carbon dioxide is an important heat trapping greenhouse gas, currently rising and threatening life as we know it on our planet. We would like to predict future levels of CO2 in the atmosphere based on the historical data provided by National Oceanic and Atmospheric Administration. The preceding chart was taken from here and the data was taken from NOAA. We will use the year 2006 as a starting point with CO2 level of 382 ppm and calculate the estimate using a simplified or optimistic linear function as follows. Estimate is equal to 382 plus year minus 2006 times 2. Create a function called CO2 estimate that takes one integer parameter called year and returns the estimate level of CO2 ppm for that year. These steps will help you complete this activity. Okay, let's follow this step by step. Open your favorite editor and look a window next to it. Okay, so let's try to open the code and let's create a new value file called, save it as, let's save it on the desktop for now and save it as, what was the name? CO2 estimate. Let's name it CO2 estimate dot CLJ, I guess, as the type. Yep. Okay, about that, it automatically opened the terminal. Start the REPL with the command start press REPL and connect. Default key bindings are REPL, jack in, Control Alt C, Control Alt G. Connect to a running terminal using Control Alt C or Control Alt C, Control Alt C, Control Alt C. So what was the, how do I get the code? That URL. Let's try to let's try to create a new workspace on Canva first. Control Shift Canva. Peer edit, clear REPL history, connect to running REPL server, run all tests. So how to create a new workspace? For now, let's forget about this. For now, just focus on solving the problem. In your editor, define two constants, base CO2 and base year, with the values 382 and 2006 respectively. I guess I should move now. So define two constants, base CO2, base year. I guess these should be global bindings. So let's create two global bindings, base CO2, which should be 382, and Does def take multiple arguments? Def x 2 y 3. Was it let? Dot Guess let can take multiple arguments, but def takes a single, or def can define a single expression at a time, I think. So this year it should be 2006. What else? You write the code to define the CO2 estimate function without forgetting to document with docstring parameter. Okay, let's define create a function called CO2 estimate, and then let's estimate the CO2 emission. Let's go with that for now. It takes in a parameter as takes in year as a parameter. Unused binding. You may return write the function body in a single line, but nesting a lot of function call declare the relative if all failure to reason about each step of the process by decomposing them in a let block. Write the body of the function using let. Define the local binding year diff, which is the subtraction of 2006 from the year parameter. Okay, let's create let year diff is equal to year minus base year. Oh, my bad. Again, old habits die hard, really. Why is it not deleting this? Huh? It's not else. So we need to minus year and this year. Year diff is not used. Test your function by evaluating CO2 estimate. You should get 470 as a result. Okay, now estimate is equal to 382 plus year minus 2006 times 2. Yes, I'll have to look at the let documentation again. Just a sec. Let, and we can do expression as well. Let defines something, and then we can use that in an expression. But what I'm trying to see if we can use multiple expressions as well. Let can define multiple things and multiple expressions. Yeah, that's what I was confirming. So we can define multiple things, but for now we've defined year diff, which is this year diff, and then we can simply use this and return it as an expression. So what we need to do is add 382 to the result of multiplying year div with 2 and return the whole thing. And we can test our function using CO2 estimate 2050. Yeah. Okay, now let's try to run all this in the record, and we get 470, which is the expected output. And if we use 2020, expected output is 410, and yeah, this is working fine. First of all, we created some global bindings with CO2 and gave them the default values. Then we defined a function named CO2 estimate, gave it a doc string as well. Its input argument is year, and then we defined a let block or let block with variable year div, which is calculated as base year minus base year, and then we calculated the result such that the 382 is added to the result of year difference multiplied by 2. That is simple. In Python I write it like def CO2 estimate here. Return simply this 382 plus year minus base year, and that multiplied by it's difficult to code Python here, but yeah, it would be much less fun, of course. Okay, we're done with that. The truth is simple. Now we're going to learn about true values, I guess, Boolean values. Up until now, we've been using conditional expression intuitively possible on the basis of the usual work with other programming languages. In this final section, we will review and explain Boolean expression and the related comparison functions in detail, starting with nil and truthiness in Clojure. Nil is a value that represents the absence of value. It is also often called null in other programming languages. Representing the absence of value is useful because it means that something is missing. If Clojure nil is falsy, which means that nil behaves like false when evaluated in a Boolean expression. In Clojure, nil is false. False and nil are the only values that are treated as false in Clojure. Everything else is truthy. So I guess this means that 0 is also 0 isn't considered false, as just like in other like in C++, etc., 0 is considered false, but here 0 won't be considered false. This simple rule is a blessing coming from such a JavaScript and makes your code more readable, less error-prone. Perhaps just that Clojure not out yet when Oscar Wilde wrote, "The truth is really pure and never simple." The truth is simple. In this we will learn how to work with Boolean values and conditional expression. We will also see how to play around with the logical operators in conditional expressions. So let's get started. Let's start by verifying that nil and false are indeed falsy. If nil, truthy, falsy, sure falsy, if false, falsy. In other programming languages, it is common for more values to result to false in Boolean expressions, but in Clojure, remember that only nil and false are false. If 0, truthy, falsy, it will be truthy, -1, truthy, empty brackets, truthy, empty square brackets, truthy. If string false, it's truthy. If empty string, it's truthy. Got it. If you want to know whether something is exactly true or false, not just truthy or false, you can use the true and false functions. True, 1, false, true. If true, 1, yes, no, no, true, true, false, true, true, false, nil, false, 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 true. It's just a function that return a Boolean value. So we have to remember this. The question mark character is a naming convention for functions that return a Boolean value. For example, if I want to see if the function is done and it returns a Boolean value, then I'll define its syntax or name to be done. Similarly, if we want to know that something is nil and not just false, we can use the nil function. Got it. No, yeah. Remember that println returns nil, and so the last piece of output in the preceding code is true. Nil. Got it. Got it. Got it. Boolean expressions become interesting when they are composed together. Clojure provides the user suspects, that is and or. At this point, we're only interested in logical and logical or. If you're looking to play around with bitwise operator, okay, and return the first false value that encounters from left to right, and will not evaluate the rest even when that is the case. When all the values pass to and are truthy, and will return the last value. Okay, experimenting by passing mix of truthy and falsy values to observe the return value that's been generated, and hello, it will return the last value. It's truthy, yeah, and truthy, and it will return the last value, and false, it will return the first false value. Let's use println to make sure that not all the expressions are evaluated. And println hello, println goodbye. So println hello, this would return nil, and nil, so it would return simply, it would just print hello and then it would return nil. And evaluated the first expression with printed hello and returned nil, which is false. Therefore, the second expression was not evaluated and goodbye was not printed. All works in a similar fashion. It will return the first truthy value that it comes across, and it will not evaluate the rest of the expression when that is the case. When all the values that pass to or are falsy, all will return the last value. When all values are falsy, it will return the last value. When it will return the first truthy value. So our truthy, first truthy value, it will first truthy value, first truthy value. Once again, we can use println to make sure that the expressions are not all evaluated or true. Println hello. Hello is not printed. The truth is really simple, in Clojure at least. Comparing values, equality and comparison. Okay, and most important is used for variable format. As we've seen already in Clojure, we have def and let to bind names with values. The equal symbol is a function for equality and will return true if all its arguments are equal. So we're not using double equal sign here. As you may have guessed by now, the other common comparison functions are implemented as functions. This is function, this. Not special syntax, and you may have developed the intuition for using them already. In this final, we will go through different ways of comparing values in Clojure. Let's get started. First, start your REPL if it's not running yet. Have the following expression to compare two numbers. 1 equals 1, 2, 1 is not equal to 2, false. You can pass multiple arguments to the equal operator. 1 is equal to 1 is equal to 1. Got it. Equal, the last one isn't, so function returns false. They all should be equal then. Not only to compare numbers but other types as well. Evaluate some of the following expressions. User nil, true, false, nil, false. Hello, hello. Dot reverse, hello, true. Got it. 1 2 3 and 1 2 3 2. In Java language is comparing things. It checks whether they are the exact same instance of an object stored in memory, that is their identity. However, comparison Clojure are made by equality rather than identity. Comparing values is generally more useful and Clojure makes it convenient, but if you want to compare identities, you could do so by using the identical function. Maybe more surprisingly, but sequences of different types can be considered equal as well. So this is a list 1 2 3, and this is a vector 1 2 3, and they're both considered equal. Collections and sequences are powerful Clojure abstractions that will be presented in chapter 2. Their type and immutability. It is worth mentioning that the equal function can also take one argument, in which case it will always return true. The other comparison operator, that is this, can only be used with numbers. Let's start with this and this. It's true. It's basically it's all very simple for now. Okay, instead of the exclamation mark, we use not symbol, or not text keyword. Only the not operator is useful in that returns true when its argument is false. Good thing to follow JavaScript code. Let x is equal to 50. Let x is equal to 50 if r is if r x is less than or equal to 1. If x is greater than or equal to 1, or let's say if x is between 1 and 100, and x modulo of x with 100 is equal to 0 and valid, otherwise print invalid. Okay, this is really cryptic looking and hard to follow around. If x is greater than or equal to 1 and then x is less than, let's do this. So here it's saying if 1 is less than or equal to x, the x is less than or equal to 100. Got it. You may have human Clojure, but you could argue that it will be more readable than the imperative JavaScript code. Really? But you could argue that Clojure is more readable than the imperative JavaScript code. It contains less specific syntax and we don't need to think about operator precedence. If we wanted to transform the JavaScript code using an inline if we would introduce new syntax with this and this as follows. Clojure code would become the following. Let x 50 print line if this then valid otherwise invalid. interesting. Let's do the activity again. In this activity, we will improve the meditate function with rotating SSI 1.05, creating simple function with fn and fn by replacing the com boolean argument with calmness level. The function will print a transformation of the string part as a second argument based on the calmness level. The specifications of the function are as follows. Okay, calmness level is a number between 1 and 10, but we will not check the input for errors. If the calmness level is strictly inferior to 5, we consider the user to be angry. The function should return the S string transformed to uppercase concatenated with the string Italia. If the calmness level is between 5 and 9, we consider the user to be calm and relaxed. The function should return the S string with only its first letter capitalized. If the calmness level is 10, the user has reached nirvana and is being possessed by the Clojure gods. In its trance, the user channels the incomprehensible language of those divine entities, the function which should return the S string in reverse. Use the str function to concatenate string and Clojure.string / reverse to reverse a string. If you're not sure how to use them, you can look up their documentation or talk. These steps will help you complete this activity. So what was the function name? Meditate. Let's try writing meditate now. Control M. Save meditate.clojure. Define function with the name meditate. So define meditate, taking two arguments, calmness level and F, without forgetting to write its documentation. Okay, so we write documentation here, and then it takes arguments, and then it performs something, and that's the whole function. Meditate returns the string, returns the transformed string based on meditate calmness level. And it takes as argument, takes two arguments from this level and S. Start by writing that prints the string Clojure meditate version 2.0. First, let's print line Clojure meditate version 2.0. Then following the specification, what do you know? Okay, following the first, write the first condition test whether the calmness level is strictly inferior to 5. Okay. Yes, we need to if condition and then expression, and if condition then first true expression, if true then false expression. So the condition is whether the calmness level is strictly inferior to 5. If calmness level is calmness level is less than 5, then write the first words of the conditional expression. If the count input of 5 we consider used to guarantee the function should return the S string transformed to uppercase concatenated. It should return yes. Let's see. So we concatenate strings with S dot to upper how did we check it real quick. Let simply difference to upper is uppercase okay doc was the thing doc find or doc doc how do we uppercase thing is there was an example here somewhere. No. There was example here somewhere. Yeah. Clojure dot string upper dash case net. So I have to type the whole thing. Upper dash case. Got it. String st. So you need to type Clojure dot string uppercase S and concatenate it with Italia. Okay. If the calmness level is between 5 and 9, we consider user to be calm and relaxed. The function should return a string with only the fifth letter capitalized. I should have looked. Closer. Clojure.string capitalize S. Okay. But so here we need to add a mistake. Which should be nested in the second branch of the 8. It should turn. So here we need to again check if the what was the second part of that? If the cumulative level is between 5 and 9, so it is less than or equal to 5 is less than or equal to commonness level, and commonness level is less than or equal to 9, then do this, else do that. If that is the case, then do what? If that is the case, then function should return the string s with only its first letter capitalized. So we can write clojure dot string slash capitalize s, and otherwise, well, we're not really checking for wrong values, but I don't know if I should just assume this to be the else statement, or should I? Yeah, let's write another if statement. If condition okay, we don't need else statement for this. If equal to commonness level 10, then we should do clojure.string.reverse s. So let's try running this. Control C, Control V. Syntax error reading source at REPL 11248. So what is the what we do now occurs in int. What might be the syntax error? Define meditate, then this, then inputs, then oh. Define. Meditate, I did. Define meditate. Let's just try it with compiling now. Such for clojure.string.capitalize. Okay. Yep. Yep. Let's try it again. Okay, it's working now. Clojure meditate. Execution error. String cannot be cast to number. Where am I casting a string to a number? String Clojure dot. Oh, need to do that. And now this will hopefully run perfectly fine. Yep. And if we go to 5, which now echoes an eternity, first is capitalized. And if we go to 10, then what we do now echoes in eternity. Yeah, that's continue.
In this exercise, we will take a look at
So look up the conditional operator in documentation and rewrite your function. Nested conditions with conditions. So don't count. Takes a set of test expression pairs to evaluate each test one at a time. If a test returns logical true, count evaluates and returns the value of the corresponding expression. Doesn't evaluate any of the other tests or expressions. So let me see if I understand it correctly. If true is true, 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 false, false, true, 3. Just run the first one. Takes a set of test expression pairs. It evaluates each test one at a time. If the test returns logical true, count evaluates and returns the value of the corresponding expression. And doesn't evaluate any of the other tests or expressions. But if we do this, then yeah, that makes sense. Let's quickly try to use conf for this. So I'm going to comment this out real quick and literally copy instead of if we use const here, and this is the condition and this is the expression that it should evaluate. Then again, this is the condition and this is the expression if it's true, and in this is the condition and this is the expression. Wait a minute. Control V, Control V. And this is the expression that it should evaluate. So it looks much cleaner, I guess. Yeah, and 6 working perfectly and 10 working perfect. Yeah, this is more succinct. Complete and continue. In this lesson, we discovered how to use the REPL and its helpers. You're now able to search and discover new functions and look up the documentation interactively. In the REPL, we learned how Clojure code is evaluated, as well as how to use and create functions, bindings, conditional when comparison to allow you to create simple programs and scripts. In the next lesson, we will look at data types, including collections, and the concept of immutability. Complete and continue. So we've been streaming for 2 hours now. I think we should take a little break, like about 5 minutes or 15 minutes, and then we will try to go through this chapter 2 of Clojure from the ground up, hopefully. So, see you in a while. So okay, we're back. So let's get started. Clojure from the ground up, basic types. Today we'll learn about the basic types and how they're represented in Clojure. We've seen a few different values already, for instance nil, true, false, 1, 2.34, MCW. So this is nil, boolean, integer, float, a double, string. Clearly all these are different values, but some of them seem more alike than others. For instance 1 or 2 are similar numbers, both can be added, divided, multiplied and subtracted. 2.3 is also a number and acts very much like 1 and 2, but is not quite the same. It's got decimal points. It's not an integer, and clearly 2 is not very much like a number. What is 2 plus 1 or false divided by 5.3? These questions are poorly defined. We say that a type is a group of values which work in the same way. It's a property that some values share, which allows us to organize the world into sets of similar things. 1 plus 1 and 1 plus 2 use the same addition which adds together integers. Types also help us verify that a program makes sense, that you can only add together numbers instead of adding numbers to porcupines. Types can overlap and intersect each other. Cats are animals and cats are fuzzy too. You could say that a cat is the member or sometimes instance of the fuzzy and animal types, but there are fuzzy things like moths which aren't animals, and animals like alligators that aren't fuzzy in the slightest. Other types completely subsume one another. All these are house cats, and all house cats are felidae, and all felidae are animals. Everything which is true of an animal is automatically true of a house cat. Hierarchical types make it easier to write programs which don't need to know all the specifics of every value, and conversely to create new types in terms of others, but they can also get in the way of the programmer because not every useful classification like fuzziness is purely hierarchical. Expressing overlapping types in a hierarchy can be tricky. Every language has a type system, a particular way of organizing nouns into types, figuring out which verbs make sense on which types, and relating types to one another. Some languages are strict and others more relaxed. Some emphasize hierarchy and others are more ad hoc view of the world. We call Clojure's type system strong in that operations on improper types are simply not allowed. The program will explode if asked to subtract a dandelion. We also say that Clojure's types are dynamic because they are enforced when the program is run instead of when the program is first read by the computer. Okay, strongly typed and dynamic. We'll learn more about the formal relationships between types later, but for now keep this in the back of your head. I'll start to work to the concept later. Let's find the type of the number. To find the type of something, we'll type 3. So instead of using int, by default it's using long, and that too of Java type long, type 3. Longs internally are represented as a group of 64 binary digits written down in a particular pattern called sign-to's complement representation. Okay, how big is this? So we can find out by going to long and long package, I guess, your long namespace, and find out its maximum value. No such namespace. Oh, sorry. Okay, and then we can try to increment it, getting the last value and execution error integer overflow. So this will give us throw an exception of integer overflow. So java.lang.arithmetic exception message integer overflow. Never occurred before the current type something. The type of error was an arithmetic exception and message was in this type of number can't hold a number that big. The error came from a specific place in the source code of the program. Numbers.java on line 1388 Okay. That's all. So later we'll learn more about how to unravel error messages and find out what went wrong. The important thing is that Clojure's type system protected us from doing something dangerous. Instead of returning a corrupt value, it reported a valuation and returned an error. If you do need to talk about really big numbers, you can use a big int, an arbitrary precision integer. Let's convert the biggest long into a big int, then increment it. Okay, yeah. Notice then at the end there's a Clojure writes arbitrary precision integers type 5 and okay. So to use big int, you just have to append n at the end of the number. There are also smaller numbers type int 0. We can typecast it. Typecast a long into an integer or a short or a byte. Right. So these are all different sizes of the integer. These are all the sizes long to store values in 32 bits, shorts, or 16 bits and bytes are here. That means their biggest values are this respectively. So the biggest value that can be stored in a byte is 127. If you go above that, it will probably give let's see, it will probably, let's first convert byte of 127. Let's first convert 127 to byte and then try to increment it, and it's going to give 128. And the reason it's going to give 128 is because when we increment it, it's converting it again into long. Let's verify it. So we increment byte 127, and yeah, it's long. But if we try to cast it to byte again, then it should give an error. Illegal argument exception value of out of range. Fractional numbers to represent numbers between integers. We often use floating point numbers, which can represent small numbers with fine precision and large numbers with coarse precision. Floats use 32 bits and doubles use 64. Doubles are the default include. Okay. Floating point math is complicated and would get bogged down in the details just yet. The important thing is float and double approximations. There are limits to their correctness. So if we type this, it will be got it. These are just approximations. We can use the ratio type. This type is not of the Java lang specific to Clojure. And then there are mathematical operations. The exact behavior of mathematical operations Clojure depends on their types. In general, though, Clojure aims to preserve information. Adding two longs returns a long, adding a double and a long returns a double. Okay, just like in Java or C++, 3 and 3 plus 0 or 3.0 are not the same number. One is long and the other a double, but for most purposes they are equivalent, and Clojure tells you so. 3 and 3 are not equal, but they are equivalent. So single equal is checking for equal, and also converting but a little more loosely. So this checks for approximation. It considers integers equivalent to their floating point represented. We can also subtract this. We can also subtract, multiply, and divide different numbers, and they'll all get typecasted. Putting the verb first in each list allows us to add or multiply more than one number in the same step. Plus 1, 1 plus 2 plus 3, and 2 times 3 times 1 by 5 times 3 is 6, or 6 times 5 is equal to 6 by 5. Subtraction with more than 2 numbers subtracts all later numbers from the first. Division divides the first number by all the rest. So minus 5, 5 minus 1, 4, 4 minus 1, 3, 3 minus 1, 2. 24 divided by 2 is 12. 12 divided by 3 is 4. By extension, we can define useful interpretation for numeric operations with just a single number. Plus 2 minus 2 times 4 by 4. You can also add or multiply a list of no numbers at all, obtaining the additive and multiplicative identities. Effectively, this might seem odd, especially coming from other languages, but we'll see later that these generalizations make it easier to reason about higher level numeric operations. But often we want to ask which number is bigger. If one number falls between two others, this means less than or equal to, and third fall in order to multiply. Yeah, we've learned all this in the Clojure workshop. Less than numbers just like this, except that no two values may be equal. So here they are equal, so 1 is less than or equal to 1, and 1 is less than or equal to. So here 1 is less than 1 false over here, but this one is true, but this one is false, so it all returns false. Difference this greater and greater than equal to specular assert the numbers are in descending order. Also commonly used are inc and dec, increment and decrement, which add and subtract one to a number respectively. One final load equality test can take more than two numbers as well. So these all should be equal. We can easily see if all the elements in a list are equal. Strings, we saw that strings are text surrounded by double quotes like full strings in Clojure, are like longs, doubles, and company backed by a Java type. And strings in Clojure are like longs, doubles, and company. What's company? Backed by a Java type. User type get java.len.string. We can make almost anything interesting with str, strings, symbols, numbers, booleans. Everywhere in Clojure has a string representation. Note the nil string representation is empty string. String get, string 1, string 2, string 1 2 3, simply 1 2 3, string that. String can also combine things together into a single string, which we call concatenation. So we can concatenate strings as well as integers together, so we don't have to typecast 3. In text, we can use a regular expression, which is a tiny language for describing particular arrangements of text, refined and rematches. Look for occurrences of a regular expression in a string. Defined a cat. So we can use refined to find some expression, a string, a substring in a string using a regular expression. Refind, we want to find cat, the cat mouse, we got cat. Refind cat on the browser .net. The is a Clojure way of writing a regular expression. So to write regular expression, you simply append the pound sign or hash sign before the string. With rematches, you can extract particular parts of string which match an expression. Here we find two strings separated by a colon. The parentheses mean that the regular expression should capture the part of the match. We get back a list containing the part of the string that matches the first parenthesis followed by the part that matches the second parenthesis. So we get anything before the semicolon or colon, no problem, and then we get anything after the everything after the colon. We get mouse and treat as a separate list. List elements are most. Regular expressions are a powerful tool for searching and matching text, especially when working with data files. Since regexes work with the same in most languages, you can use any guide online to learn more. It's not something you have to master. Boolean and logic, everything Clojure has a sort of charge. Truth value is sometimes called truthiness. True is positive and false is negative. Null is negative too. Boolean true, Boolean false, Boolean no, Boolean 0, Boolean 1, Boolean hi there. Everything else is positive or true, as we learned in the workshop already. Using and or not, and return the first negative value or the last value of all are true. And true, false, true. So it will return the first negative value or the last one, and 1, 2, 3 the last one, or return the first positive value 2 or the last one nil, and not inverts the logical sense of a value. Symbols. If you saw symbols in the previous chapter, they are the bare strings of characters like foo or plus. So this is a symbol. str is a symbol. Symbols can have either short or full names. The short name is used to refer to things locally. The fully qualified name is used to refer unambiguously to a symbol from anywhere. If I were a symbol, my name would be Kyle and my full name Kyle Kingsbury. For example, here it is the short name str and the full name is clojure.lang. No, this is let's see, ink. Yeah, short name is ink and the full name is object.clojure.code incorporated. But yeah, I guess this is the full name along with this, or this is the full name. The job of, when we talk about the maximum size of an integer, that was a fully qualified symbol to type integer max value clojure.lang.symbol. So here the symbol string is the same as clojure.core.string. It's the short name and this is the full name. The job of symbol is to refer to things, to point to other values. When value symbol is looked up and replaced by their corresponding values, that's not only the symbol but it's the most common use case. Keywords. Closely related to symbols and strings are keywords which begin with colon. Keywords are, let me quickly see what's a colon and semicolon, because I keep getting these two mixed up. Keep mixing. Colon, this is the colon and this is the semicolon. Got it. These are columns. Closely related to symbols and strings are keywords which begin with a colon. Keywords are like strings in that they're made up of text but are specifically intended to use as labels or identifiers. These aren't labels in the sense of symbols. Keywords aren't replaced by any other value, they're just names by themselves. Like map. Keywords can also be used as vertical with specific values and other data types. So these are keywords. Name, date, string, date, type. List. A collection is a group of values. It's a container which provides some structure, some framework for the things that it holds. We say that a collection contains elements and numbers. We saw one kind of collection, a list, in the previous chapter. This is a list, and by putting this before 1, 2, 3, it doesn't evaluate it and simply returns it. Clojure.lang.persistent list. Remember, we code lift with it to prevent them from being evaluated. You can also construct lists using list function. Lists are comparable just like every other value. List 1, 2, 1, 2, they're equal. You can modify a list by conjoining an element onto it. Conjoin 1, 2, 3, 4 and 4. If we add it to the start, we added 4 to the list but appeared at the front. Why? Internal lists are stored as chains of values. Each link in the chain is a tiny box which holds the value and a connection to the next link. This data structure, called a linked list, offers immediate access to the first element. But getting to the first element requires an extra hop down the chain. First list 1, 2, 3, 1, and the third element after that, and so on. Nth element gets an order collection. Why is there was no data for 1? Okay. Constant vector adds to the n, not the start. Our friends first, second, and nth work here too, but unlike left, nth is fast in vector. That's because internal vectors are represented as a very broad tree of elements where each part of the tree branches into 32 smaller trees. Even very large vectors are only a few layers deep, which means getting to element only takes a few hops. Okay, so I thought it would internally be stored as an array, but still it's being stored as a tree, but a very branched out tree as compared to a deep tree. First derivative is to be rest 1 to 3, it would give us 2, 3, and next 1 to 3 it would also give us 2, 3. Rest, right. So rest and next first gives us the first element in the vector or list or set, and next give us everything except the first, and rest also gives us the same thing, but if the list is empty then rest gives us an empty list while next gives us a null value. That's the difference, otherwise they're exactly the same. Ref returns logically true, next returns logically false. Each has their use, but in almost every case they're equivalent. We can get the final element of any collection with lost and figure out how big the vector is with count. So count 1, 2, 3, size as 3. Because vectors are intended for looking up elements by index, we can also use them directly as verbs. So vectors are intended for looking up elements by index. We can also use them directly as verbs. A, B, C, and 1. So it's returning B. But it's zero-based indexing, so index out of bound 2, it will return C. Got it. So we took the vector containing 3 keywords and asked what's the element at index 1. List, like most but not all modern counts up from 0, not 1. Index 0 is the first element, index 1 is the second element. Okay, this is a zero index based language. Equal in Clojure. Okay, lists and vectors, if they are have the same elements, then they're considered equal. Sometimes you want an unordered collection of variables, especially when you plan to ask questions like, does the collection have the number 3 in it? Clojure, like most languages, calls these collections sets. To create a set, why not just use this map literal? Okay, that's probably being used for maps. So for sets we use a pound sign and then the elements in the sets which will be unordered. So for example, I inputted in the order 1, 2, and 3, but it's being stored as 1, 3, and 2. And let's try to branch the last output, and let's try to add 4 and 1432. Okay. Adds an element or offer elements in sorted order. We can sort these sets from the left of vector. Order, we will ask it as a list or vector. Okay. So if we call sort on it, it will return a sorted list. It's not set now, it's a list. Conjunct set adds an element. It would add wherever it wants, A, B, C, but it won't contain the same element twice. Sets never contain more than one, so which does nothing. Conversely, one removes elements with disjoint or disconjunction or I don't know what it stands for. The most common operation with a set is to check whether something is inside it. For this we use contains, and because we're checking for a boolean, its syntax says according to the naming convention used in Clojure, we append a question mark at the end. Contains 3 true, contains 5 false. You can use the set itself as a verb, unlike contains the expression returns the element itself. You can use the set itself as a verb. Return the element itself if it was present or not. Okay, so if the element was present and we're trying to see if 3 was present, then if it returns some element like 3 or if it returns the same element, then that means that it was present, but if it returns null, then that means the set doesn't contain that element. And we can use the set function to create set from any other collection like vector or list. The last collection on our tour is the map, a data structure which associates keys with values. In a dictionary, the keys are words and the definitions are the values. In a library, keys are called signs and the books are values. Maps are indexes for looking things up and for representing different pieces of named information together. Here's a cat. Users. So where if you come from Python especially, there it's represented as a dictionary, and there the syntax is kind of like name, and here I have said this is my name and then another keyword. I keep forgetting, was it name in this? Yeah, but here we are specifying a keyword, for example name, and we're specifying a value mittens, binding that value to the name keyword, and same weight has the value 9 and color has the value black, and it will be unordered, but it doesn't matter in this case because usually we index it by using the key name. Maps are surrounded by braces filled with alternating keys and values. In this map, the 3 keys are name, color, and weight, and their values are mittens, black, and 9 respectively. We can look up the corresponding value for a key with cat. Cat, dog, cat. So in this dictionary, if we get the value cat, it would get the key cat, it would return the value mu that's associated with the key cat. And if we try to get something that isn't present, it would return nil. Get Linda, good, wicked, not here. Get, this is the get contains the default value to return instead of nil if the key doesn't exist in that map. Okay, so this is the default value if this key doesn't exist here, so it won't return nil, instead it will return this default value. Since lookups are so important for maps, you can use a map as a verb directly. Yep, just like sets or vectors. And conversely, keywords can also be used as verbs which look themselves up in maps. That's true. So we can try to look see if raccoon is present, and if it is, then we will return the value associated with raccoon, that is king. We can add a value for a given key to a map with sock associate, I guess. So here this is the map or dictionary, and we're adding camshafts 3 to this dictionary. So this will add this. Similarly, we can update it. For example, before camshafts was 3 and now we can update it to 2. If key isn't present, it adds the key and value. If it is present, then it updates the value. And if you associate to nil, it creates a new map. Got it. And we can use merge two different maps. For example, here A1 B2, but B will become 3 because it's being merged with this, and C will become 4. C4 A1 and B3. Finally, to remove a value, you use this sock, right sock, this sock. There was also something disjoint and conch. Disjoint, conch, sock, this sock. So we'll have to keep in mind all these function names and what they do. All these collections and types can be combined freely. As software engineer, we model the world by creating a particular representation of the problem in the program. Having rich set of values at our disposal allows us to talk about complex problems. We might describe a person, name, a million, hard birth, this, death, or a recipe. Yeah. So this is a map. This is map. This is what a map is of. And then this is a list. No, this is an expression, and this is a vector. This is a vector. This is a vector. Yeah. This is a map, whole map, and on the Afghanistan key we have another map within map. Okay, so yeah, this is basically it. So we learned today we learned about some basic data types like integers, strings, and fractional numbers, and mathematical operations and comparison operators, as well as operations on strings and how to find something. Then we'll learn about Boolean logic, and, or, not, etc. Then we saw what symbols are and what keywords are. Then we briefly looked at lists and vectors and sets and maps. And this is the first chapter basic type, Clojure from the ground up basic type chapter. And we also finished 2 modules in the Clojure workshop book as well. So, and here we can learn quite a lot. This is quite fast-paced, and I think I like fast-paced thing better. And yeah, we learned about if and do and when and what are forms, etc., and how to define functions and what are blocks and global and local bindings, etc., and comparing values, and wrote some simple programs. So I think it's enough learning for now. Let's some practice examples, or should we do this as well, or should we do it at a later session? How about let's quickly go to the next chapter and see what are its contents, and then we will go through some of these foreclosure problems. So here we'll learn about leg bindings, functions, calling functions, defining functions through fn, then variables, vars, using defining functions, defn, and I guess we've covered a lot of this in this first module here, but still we'll go through this again, as we might find some new information very deep in this documentation. So let's try to go quickly go over these one by one. So equality, to compare equality with true, we simply give it the true value, or let's say if this would run as well, but 1 equal to, oh yeah, it won't run. It's not checking truthiness, just checking with the truth value or true keyword. Simple math, intro to string, intro to list, let's conch. Simple math, yeah, 2 by 3, 3 to the 6, and then we 10 minus 6, this would give us 4, and that's the correct solution. Again, we did this yesterday, we also did that yesterday, and this as well. Next, intro to vectors, vector cons, intro to sets, sets cons, intro to maps, map cons. Okay, vectors can be constructed several ways. You can compare them with this. Know the brackets surrounding the blanks are part of the test case. I guess we did that yesterday as well. Yeah, and yeah, we did that as well. Sets are a collection of unique values. So set of a b c c c d d and Clojure.set union a b c and b c d. This would all result in a new set which is a b c d. Both will result in a new set, and we can define a new set using this notation. And when operating in a set, the const function returns a new set with one or more keys added. 1 4 3, 1 2 3 4. So what's the missing here? 1 2. If we add 2 here, it would result in a set that contains 1 2 3 4. Maps store key value pairs. Both maps and keywords can be used as lookup functions. Commas can be used to make maps more readable, but they are not required. So commas are optional. Hashmap. Okay, we can. Thought we could use map to map different things, but it's not map, it's Hashmap. A1. Yeah, it's Hashmap. Or we can simply do A1 and B2. Yeah, commas are optional. So here we're creating a hash map with key A value 10, key B value 20, C and 30, and we're getting the B key, or asking for the value of B key. B, same, we've seen these two syntax alternatives in the lesson today. In the new map within key payloads array. So here we're A1, B2, C3, const A1, and here we'll append b2, but let's make it b2 and see if it works. Most probably it will work. Let's try. Return a new collection with x added, column x, column x. That takes a list. Yeah, my bad. So here it's conjugating or adding to this dictionary and adding what? B and 2 and C and 3. But can we add those in a same using the same single vector? Nope, must be a pair. But maps done. We'll do the rest in another session, so I think it's fine for now. Let's summarize what we learned, and probably, yeah, it was a fun experience for me, and I'll probably stream tomorrow, inshallah. I'll see if I start learning, or if I'm in the mood to learn Clojure further, then I'll probably stream today as well. I'll let you know, guys, on Twitter. So till now, Allah Hafiz.